So what is chemistry? Well, that's not the easiest thing in the world to answer. The sciences, philosophy, things like that, they aren't as separate as people might want to hope. Okay, I mean, over here you have philosophy. Okay, over at one, if you analyze the words, you break it down. Philo means love. Sophie, that's from Sophos, means love of wisdom. Okay. And over at the other end, you have science, which, again, foreign word, just means knowledge. So, frankly, philosophy and science, they're both very pretentious ways of talking about the same thing, love of learning, wanting to learn things. And they're really not that separate. They're not that different. The difference, the separation, no, they're not separate. They're not different. They are connected. They are on a spectrum. Science on one end, philosophy at the other. And philosophy is science with less data. And science is philosophy with more data. Okay. They're pretty much the same thing. You do one, you're doing the other. The difference is that scientists are delving into minutiae of the real world, of the physical world, I should say, and they are working with lots and lots and lots of concrete information. Philosophy is, just more abstract, and they're dealing with the less concrete sorts of things. So when you do one, you're doing the other, and they have to be connected. You have to do both. Okay. Philosophy without science, it has to have a grounding in science. Okay. Philosophy, if it's not grounded in science, is going to be worthless. Okay. It needs a scientific foundation. Okay. But at the same time, science also needs a strong grounding in philosophy. It needs a good philosophical foundation. The philosophy of science is what guides the science and makes it work. It needs the philosophy. You do one, you're doing the other. If you're doing philosophy without good science, then the result is going to be pretty much worthless. It's like expecting a random number generator to work as a good clock. Likewise, science that isn't working off of a good, solid foundation in philosophy is going to just head off in wild, random directions. It's not going to have the proper error-correcting mechanisms. It's going to explore things that really aren't worth consideration. They're just impossible. Or, on another plane, it could head off in just god-awful, entirely immoral directions. The scientific racism of the 19th and most of the 20th centuries was grounded in very, very bad philosophy. And the philosophy that supported it was grounded in just awful, awful science. You need both to be good in order to get something worthwhile. So chemistry is a branch of science, but even putting it that way doesn't really describe it all that well. So you have, say, the physical sciences over here. That would be physics and chemistry. You also have the life sciences with biology and environmental science. And you have, say, earth and space sciences, which gives you geology and astronomy. But the reason I say it's inaccurate to call them branches is because they're not actually separate. They blend into one another at the edges, and you need an understanding of the other so-called branches in order to really have a good understanding of that particular field. Physics and chemistry, at the places where they butt up against one another, you have, physical chemistry is the branch of chemistry that is very, very much like physics. And then you have chemical physics. is the branch of physics that deals most specifically with chemical sorts of things. Similarly, you have biochem and organic chemistry and molecular biology are all sort of running around in the same area. And also, you want to be careful about Googling this because you'll get a lot of nonsense, but there is, a sort of a field with a lot of trouble getting away from Deepak Chopra and stuff, quantum biology. That is to say, exploring how quantum mechanics, which is both physics and chemistry, how that interacts with biological systems. You can't really understand, you can't have an adequate understanding, or a full understanding, I should say, of photosynthesis without quantum mechanics. Because that is a cascade of energy transfers from molecule to molecule to molecule that can only be understood through quantum mechanics. Similarly, geology has geochemistry, and there's geophysics, astronomy, and there's stellar chemistry, stellar physics. There's all sorts of things like that. Really, the difference between the different fields of science is more a matter of scale. It's a matter of size, the things you're focusing on. If you want to have a full understanding of things, you can focus on say, there's some space here. You can focus on, the subatomic particles, but, focusing on the subatomic particles, muons and gluons and all the other tiny, tiny, tiny super subatomic particles isn't going to really help you understand chemistry, which is focused on, electrons and atoms and molecules. And that's not really going to help you understand, at that scale, you can't understand, what's known as bulk properties, the behavior of objects. And even that isn't going to help you understand, say, individual animals. Actually, heck with animals. That's not going to help you understand tissues and organs and so on, which is necessary, but to understanding, an individual organism, an animal, let's go with organism. You need to understand tissues and organs, but at the same time, you can consider the organism as a whole without really thinking about the tissues and organisms as individual things. You can look at the behavior of the wolf without actually ever considering its stomach or its liver, and at the same time, you can consider, whole populations, coming back up here, without really thinking about the individual organisms. And from there, you can go to a whole ecosystem, and then from the ecosystem, you can consider, planet, and then solar system, or galaxy, or universe, or the cosmos, and somewhere in here, you can probably toss economics. The dismal science is somewhere sort of like a population, a study of population behaviors. Science is all about just a system of scales, what you're considering at any given time. And chemistry is sort of down here toward the smaller end. It's somewhere, in between the bulk properties of materials and subatomic particles. Okay, we consider the behaviors of, at its smallest, individual electrons, up to, actual, bulk objects and behaviors of whole physical systems, liquids and solids and so on. So that's more or less what chemistry is. It's kind of at the scale in between physics, I should say particle physics, and biology, microbiology. Giving something of an overview of what we're going to be covering, what sorts of things chemistry looks at. We look at the behaviors of electrons. That's my symbol for an electron, E-. An electron, they have their own very strange behavior. We build up from electrons and other subatomic particles, protons and neutrons. We build up to atoms. And from individual atoms, we build up to molecules. And from molecules, we're going to build up to extended I should say, physical systems. Okay? Collections of molecules. Okay? Real things. A balloon full of air, a beaker full of liquid, that sort of thing. So to sort of differentiate it, we consider how, these small objects move through space. Subatomic particles, atoms, molecules, how they move through space, not how billiard balls move through space. That's physics. They're related, they're similar, but we're not going to study them in quite the same way. When we look at, our extended physical systems, we'll go, or chemistry at least goes as far as, organic chemistry and biochem and so on. But we stop short of, moving into the realms of, we don't get too large. We don't consider the entire cell, maybe just systems within the cell. We'll talk about, the Krebs cycle, or the tricarboxylic acid cycle, or however you know the name. But we won't look at the entire mitochondrion, that sort of thing. All told, chemistry, it's you get a little bit messier than physics. It's a lot cleaner than biology. And it's a heck of a lot more indoors than your earth sciences. So the things we're going to be doing in lab, it's going to be some more sloshy liquids than what you might find in a physics lab, fewer pig guts than you'll encounter in a biology lab, and less time walking around outdoors and playing with rocks than you get in geology. And one last thing to cover here. What is a theory? Every profession has its jargon. Okay? So, mechanics have things like an oxygen sensor, or a camshaft, right? A lawyer is going to have something like res ipsa loquitur, or party of the first part. Sailors are particularly infamous for this. They'll have something like a foretopmast back preventer staysail, or jib halyard, or keel, right? It's just that every profession, every hobby, every branch of life, it's going to develop, its jargon, or its argot. Those are just, those are fancy terms. Those are specialized terms. Those are jargon for, specialized vocabulary. Okay. And some vocabulary moves in and out of those specialized fields. I mean, that's how language evolves, is when slang or jargon moves out of one subculture into another subculture, or just into another culture entirely. Okay. You can think probably in your own lifetime of different bits of slang that have gone from internet subcultures into the mainstream, or out of rap music, country, or almost anything, out of any subculture into the mainstream, and become part of the broader vocabulary. Science is no different from any other profession or subculture in this regard. And theory is part of science's vocabulary, part of its jargon, okay? Part of its lingo. Okay? So, something to consider is that theory is one of those things that has moved into the mainstream. Okay, remember, science wasn't always really part of the popular consciousness. Not until World War II and, the atomic bomb did science really start to become popular in that way. But when it did so in a big way. But the way people use theory in the common parlance is basically a guess. And you know what? That's fine. It works, for common parlance. But in science, it has a very, very different meaning. It's not a guess. Okay. In science, a guess would be a hypothesis. Okay. Thesis means just a statement. a sentence, a phrase, a statement, a declaration. Hypo means weak. Think hypothermia, right? Not enough heat. You're dying of cold. Okay, so a hypothesis is a weak statement. That's a guess. Okay, a theory is not a guess. Okay, a theory is very, very not a guess. In science, okay, you start with facts. Okay, you have to collect, billions of facts over a very, very long period of time before, you can move on from that. It often takes decades or even centuries, depending on, what area you're looking at, to build up enough facts to get to, so that's level 1, to get to the next level, which is laws. Okay, laws are built up of facts, and they are they describe patterns. Okay, they describe how facts relate to one another, how different properties, how different things relate to one another. Okay, and once you have a bunch of laws, once you have several laws, what you do is you fit them together in a framework, and that framework is your theory. That framework is the explanation. The theory explains why the laws behave the way they do, why the facts fit together the way they do. Okay, so the theory is the highest order of understanding. Okay, you go from facts to laws to theory. Okay, theory is not a guess in science. Okay, it is the best thing. It's the thing you really, really hope for. So, just to give you a couple of examples, the scientific revolution, kind of started in 1500 when cheap paper and the printing press and movable type came to Europe, and it took a couple hundred years. 1800 basically. Well, let's call it late 1700s was when we got atomic theory, thanks to some English guy. Okay, atomic theory, was built on, look at this, hundreds of years of, literally centuries of observation, by people collecting data about chemistry and making observations and publishing and sharing their information with one another. And, once that happened, they saw all these facts, these millions of facts about all these elements, and they built up into, the various laws of atomic theory. And then, only then, did we actually get the atomic theory. Okay. And having the atomic theory, we were able to, work with that. Before that, it was not really known whether or not atoms were even real. Okay. And since atomic theory was first proposed in the late 1700s, we've updated a bit, we've made some changes, but the core of atomic theory has remained the same. Matter is made up of elements that are composed of atoms. Atoms are all the same, except they're different. All these different laws of atomic theory. We've made a few modifications, but atomic theory has largely remained unchanged. In the same way, in biology, in the late 1800s, again, after centuries of observation by biologists, it was just, a little bit more difficult. They had to go out into the world and collect lots and lots of data, lots of information. But in the late 1800s, we got, evolutionary theory, the theory of evolution by means of natural selection. And again, evolutionary theory has been updated. In the early 19th century, they added, genetic elements, and then the discovery of DNA really nailed down the mechanism of heredity and things like that. We've updated it, we've expanded it, we've made a few changes. But really, evolutionary theory is even more solid now than when it was proposed in 1850. And in the early 1900s, we got relativity and we got quantum mechanics. Okay, two theories about the way space and matter and so on act and behave and interact that they've been updated, they've been altered a little bit. Einstein didn't get it perfectly right with relativity. Pauli and the many others who developed quantum mechanics didn't get it perfectly right. We've been making updates, we've been changing it, and we know that we're going to find some really big update in the future, because right now, these two don't mesh. So we're not done. But at the same time, whatever we find that brings these two together, it's going to be a change. It's going to be a big change. But whatever is true now is still going to be true. These two theories will still be fundamentally sound. We're just going to have to find some update, some patch that's going to bring them together. So these are all theories, and none of them are guesses. Okay, we are certain about atoms, we are certain about evolution, we are certain about relativity and quantum mechanics. Well, we call them theories because the scientific jargon, the word theory, means something different from the common use of the term of theory. Maybe I should use a different word than common. I don't mean like nobility versus commoners. Maybe mainstream versus subculture. Scientists are sort of like hipsters in that way. In that we have funny haircuts, wear glasses, and are usually a couple decades out of date in our clothes. Okay, they're not that bad. Some of them are. Not all of them. A lot of them. Not all of them. And that's all I wanted to cover with this little set of lectures. Okay, what is chemistry? What is a theory? See you next time.